And then underneath that, I reminded you that we have two equations with the small letter c in it, and they're different. So you just have to keep track that when you do mc delta t, that is the specific heat capacity, has nothing to do with speed of light. And when you do E is equal to mc squared, then that has to do with the speed of light. And so basically, I highlighted the speed of light 3 times 10 to the 8. And so what this whole thing was these guys thought, okay, there must be something up in space, and we're going to call it ether. And what they did is they designed an experiment to measure the speed of light relative to the ether, kind of like, you know, when we talk about normal things that we think of. If I'm traveling, like, if I'm walking on a train and the train's traveling at 10 meters per second and I'm walking with the train at 1 meter per second, I actually look like I'm going 11 meters per second to a guy outside the train. If I'm walking in the opposite direction, I'm walking 1 meter this way and the train's going the other way. Outside it looks like I'm going 9 meters per second backwards, or to me. So they thought, okay, light must do something like this too. So they designed this experiment to show that the speed of light would change. And they were expecting to find a difference in measuring the speed of light depending on how they set up their apparatus. And it turned out that the great importance of this experiment was it failed to show anything. And that is called the null. Null means nothing, the null result. The speed of light was the same no matter what they did. And so that's kind of a theory thing that you'd be expected to know on the test, like what was it called that their experiment was the null result or whatever. So that's meant that the speed of light never changed. And so Einstein came along and said, okay, well, we have to think about how that applies to things. And so first of all, he thought up something called special relativity. And again, you have to know what special relativity is based on. And it is based on that anything moving uniformly in the same frame of reference, the laws of physics apply the same. And so what do I mean by frame of reference? For example, when you're riding in a car on the freeway, everybody in the car looks like you're just sitting there. But you're actually traveling down the freeway at 100 kilometers per hour. We feel like we're just sitting here in the classroom, we're all sitting still, it's kind of boring, but we're actually flying through space, whizzing around the sun, wobbling along, turning around the Earth this way and going around this way, and we're like zooming along in space. We don't feel like it because we're in the same frame of reference. If one of us were standing on the moon, we'd be like, hey, look, there you go, bye, or whatever, or Pluto or whatever. So if you're in the same space and place, and you're traveling uniformly, the laws of physics apply to all of us. And it turns out that the speed of light doesn't change no matter what. And so that's confusing because if you start trying to look at it from different perspectives, you get an oddity. So let me just maybe do this first. This. So simultaneity is something you absolutely have to know, and I think there's a 2-mark question on the test about this, and I'll redraw the pictures on the board in a minute. But let's have a look at what this is, the initial part of his theory of relativity is.
Imagine 2 observers,
They look creepy,
one seated in the center of a speeding train car, and another standing on the platform as the train races by. As the center of the car passes the observer on the platform, he sees 2 bolts of lightning strike the car, one on the front and one on the rear. The flashes of light from each strike reach him at the same time, so he concludes that the bolts were simultaneous, since he knows that the light from both strikes traveled the same distance to his eyes at the same speed, the speed of light. He also predicts that his friend on the train will notice the front strike before the rear strike, because from his perspective on the platform, the train is moving to meet the flash at the front and moving away from the flash at the rear. But what does the passenger see? As her friend on the platform predicted, The passenger does notice the flash from the front before the flash from the rear, but her conclusion is very different. As Einstein showed, the speed of the flashes as measured in the reference frame of the train must also be the speed of light. So, because each light pulse travels the same distance from each end of the train to the passenger, she can only conclude one thing. If she sees the front strike first, it actually happened first. Whose interpretation is correct? The observer on the platform, who claims that the strikes happened simultaneously, or the observer on the train, who claims that the front strike happened before the rear strike? Einstein tells us that both are correct within their own frame of reference. This is a fundamental result of special relativity. From different reference frames, there can never be agreement on the simultaneity of events.
Okay, so what the test question will be like is one of these two situations. Let me see if it's going to write. It's going to write. Maybe. Okay, so what I'm going to do is I'm going to draw one of these two diagrams and ask you what each observer sees. So first possibility, and this is my very rudimentary drawing. Let's say I've got a rail car, and here's a person. And here's a light. And here's a light. And this is zooming along this way. And as it passes this person, so what I'm going to call this is, I'm going to call this observer 1 and observer 2. And what I want to know is, in this instance, if I turned on the lights, what would these people see? This person, because they're in the same frame with the lights, they're going to go on, they're going to see them at the same time. Because the train is moving this way, as it's coming, this person will see light 1 first, or A, and light B second. Because because it's over here, A, B, and it's coming this way, and A is closer. So I'll have a picture like this, and it'll be A, B, C, D. Which one of these is true? Observer 1 sees the lights at the same time. Observer 2 sees B first and then A. Observer 2 sees them both at the same time. Observer 2 sees whatever, right? That. Or I will draw it like this. That's a bad light. And A, B. Now, these are all outside together, just sitting in the grass or whatever you want. So as this guy's moving, this observer will see A first because he's moving towards it, and then B. This one will see them both at the same time. And my answer, A, B, C, D, will have any combination of those, and it'll be one of those. And then it'll be a 2-mark question on the test. So you need to make sure it's like, okay, I've got the 2 possibilities and what the answer would be. So as long as you're good with that, then that's the first part. Okay, so then we need to go to here. And that's kind of like this cartoon. If these two guys, A and B, are going toward each other, A maybe thinks he's at rest and B is flying by, but maybe B thinks she's at rest and A is flying by, and who's really moving? When you're in space, if there's nothing to compare to, it's all relative. So they're both right in their own frame of reference. So what happens is, if the speed of light never changes, in other words, if velocity is absolute, that's what that means, speed of light never changes, then distance and time can't be absolute. So, because v is equal to d over t, we have to have time changing and distance changing. So let me just go here. I think
spaceships are traveling together through the galaxy at close to the speed of light. Mounted on one ship is a laser that can fire pulses of light, and on the other, a mirror. The pilot of the first ship fires a pulse at the mirror and watches as it is reflected back. A clock on board measures how long the round trip takes. But now suppose that he does this as the ships are passing an observer on a nearby asteroid. According to relativity theory, this observer sees the pulse moving through space at exactly the same speed that the pilot does, namely the speed of light. But he also sees the pulse traveling a longer distance, because from his perspective, he must add the forward motion of the ships to the motion of the pulse between them. So he measures a longer time interval for this round trip than the pilot does, because he's watching the pulse go farther without going any faster. This effect is called time dilation. If two observers are moving with respect to one another, each perceives that the other's time is flowing more slowly.
So this is where we get into the time thing and it hurts your brain. So the bottom line is velocity, the speed of light is fixed. That means distance and time have to change. And so time is not the same in all frame of references. And so here's my little story of the twins. So one twin wants to travel in space, and he figures the trip is going to take 50 years, and they were both 25 years old. And they knew that when they returned, they would be 75, and neither wanted to make the journey. So one of them decided, all right, I'll go. And that obviously it's hypothetical because nothing travels at just under the speed of light. But suppose one guy was traveling at the speed of light. 50 years on Earth went by. The twin that stayed on Earth was 25 plus 50, 75 years old. And his brother steps out of the spacecraft, and he'd been gone like 2 hours. Literally, in his body and his mind, he's like, what the heck? So different frames of reference pass differently depending on how fast you go. So the bottom line is the faster you travel, and the more massive you become, the heavier you get, and the slower time goes. So if you travel at nearly the speed of light, and you're on a ship, a rocket ship, only an hour or two, a couple of months will go by, and it could be 200 years on Earth. Now, why don't we even notice this? Because it's hard to go the speed of light on Earth, right? You have to be going about 7.5 times 10 to the 7, 25% of the speed of light, before it even kind of starts to become significant. That's really impossible to do. Although I did tell you about those two guys with the jet airplane, where they synchronized the two clocks, put this one clock on a jet, it flew around the Earth and the other one sat here, and when they landed, the two clocks were different. They had to use 8 decimals or something, or whatever. The bottom line is that there's these formulas, m equals mo over 1 minus v squared over c squared. C is always the speed of light. Time is t over 1 minus v squared over, so they're the same kind of thing, right? The mass and the time formula are exactly the same. The length one is different because I take the length and I multiply it by 1 minus v squared over c squared, take the square root. It is called time dilation, means time goes slower. Length contraction means that the length gets shorter. And so the faster you go in a particular direction, the shorter that thing seems. And that makes, to me, I can visualize it, makes sense. You've got an object moving this way, and if it's a fat thing, but it's going so fast, it's almost like you don't have time to see the whole thing. It doesn't change this way, so let me just show you this. So Einstein's theory of relativity, this is just a little, your clock's running slow, no, yours is running fast, it's like whatever. So slideshow, okay, so here's what this little spaceship looks like moving at 10% of the speed of light. Nothing. It looks normal because it's not going fast enough. So then, what if we move it at 86% of the speed of light? Now it looks shorter. It's still as high as it was, but it's shorter. Now what if it was moving at 99% of the speed of light? it's still the same height, but in the direction it's moving, it's squished. And now what if it was almost at the speed of light? It would just be like this blur, a straight line. So if the spaceship is 200 feet long and 40 feet high, and it's moving by you in the direction of its length, its height never changes, and with each percentage of change in speed of light, I've just done a little calculation. If I'm going 10% the speed of light, it changes by a foot, appears, doesn't squish, and if it's going at 99.99% of the speed of light, the 200 feet thing changes to 3 feet. So think of that as like a meter. So where that is we come back to here, and we have these formulas. Now the only trick with these formulas is that the words in the question, I can't just easily say every time they say the original, like I like to think of Emma as the original.